melting in the sun, but in the shade it's actually not so bad. Okay, so we have one talk this afternoon before everybody heads over, or we have a poster session after this, and then everybody will head back over to the other. You guys will swap rooms today for the hands-on session, so everybody who did Exofast yesterday gets to do Vespa today, and vice versa. So I'm really happy to introduce Heather Knutson, who is here at Caltech, and she's going to tell us about spectral retrieval, or I have a spectrum, now what? So,
all right, can you guys hear me okay? Excellent. Yeah, so this is not really a conference about planetary atmospheres. I think, you could have a whole workshop just on that. So Travis and I are kind of, shoehorned at the end. So this is your, super condensed dose of atmospheres for the workshop. Since Travis already talked about directly imaged planets, I'm going to draw my examples in my talk mainly from transiting planets. But my goal in this talk is also to sort of more broadly discuss kind of what are the pieces you need for models and how do you compare models to the data in a way that's sort of broadly applicable to any spectrum of any kind. So one thing I think we should keep in mind with all of this is that most of the time the information we have on any individual planet is extremely limited. So we're usually in a situation where the interpretation of the data can be very degenerate. The amount of information that data contains can be very small. And so the real value of exoplanets is not in our understanding of any individual planet, but rather in the sort of ensemble of planets that we can build up and the patterns that we can see in that ensemble. So we're collecting sparse, poorly constrained information on a bunch of individual planets and hoping that if we pile enough of them together that we'll see from 30,000 feet some sort of pattern beneath us that tells us something about how planets form and evolve. So, types of questions we might want to answer with studies of exoplanetary atmospheres, other than is what I have found actually a planet? That's one question, but assuming that you know it's a planet, you might want to know something about where that planet formed, whether or not it migrated, how its atmosphere might have evolved, particularly for a close-in planet, whether it's lost a lot of its atmosphere, and those are all questions that we can answer by studying the atmospheric compositions and properties of these planets. But the key is that we're building up big ensembles of not so well constrained observations. And the nice caveat to that is that at least for transiting planets, we hope that that situation will change appreciably when JWST launches, that we'll be in a situation where we can make actual well-constrained inferences about individual planets with the beautiful spectra from James Webb. Okay, so just a super quick review. So you guys have talked earlier in the week about transiting planet surveys. One of the really valuable things about transiting planets is that it's not just a technique for detecting planets, it's also a great way to characterize them. So this is just a sort of brief overview of some of the different ways in which we might characterize the atmosphere of a transiting planet. So the first thing we can do is we can look when the planet passes in front of the star. So if the planet has an atmosphere, that atmosphere will be opaque at some wavelengths and transparent at others. So the amount of the star's light that the planet blocks will vary as a function of the wavelength that you're looking at. So that wavelength-dependent transit depth tells you something about the properties of the planet's atmosphere. If you wait approximately half an orbit, the planet's going to go around and it's going to go behind the star in what's known as a secondary eclipse. So most secondary eclipse observations focus on infrared wavelengths, where you can detect thermal emission from these planets, which typically are quite hot, 1,000 to 2,000 Kelvin. So you don't have to go that far in the infrared to pick up that thermal emission. And if you make that measurement again at a range of different wavelengths, you'll see the thermal emission spectrum of the planet. So you can look for molecular absorption or emission features. You don't have to have a transiting planet to study its atmosphere. There's now a growing body of work focusing on using variations as a function of orbital phase to detect light from exoplanets, short period exoplanets. And so examples of that include infrared phase curves from Spitzer, but also reflected light phase curves that tell you about how the properties of the planet vary from the day side to the night side. So not only are we examining kind of the bulk properties of the planet's atmosphere, we can also in some cases try to map out sort of spatial variations in the atmosphere. And that's really important for close-in planets because we think that most, if not all of them, should be tidally lost. So they're going to have a really hot day side and potentially a quite cold night side. And that can give you very fast winds in the atmosphere. It can lead to chemical gradients. There can be all sorts of variations. So a planet is not a perfectly uniform, well-mixed single atmosphere, that you can have different regions of the planet that have different atmospheric properties. Okay. All right, so just to sort of mention this last technique, that you don't have to have a transiting planet in order to characterize its atmosphere. I think, so I was just at the Exoplanet 2 meeting a couple of weeks ago in Cambridge, and one of the really sort of themes that stood out in terms of the new research that people were presenting is that this technique of actually detecting the sort of Doppler shifted absorption or emission lines from the planet is becoming a really sort of like rapidly growing and surprisingly versatile way to detect different molecules and atoms in the planet's atmospheres. And so there's a couple different variants on this, but the basic idea is that just like if you have a stellar binary, if you have a planet orbiting a star, the star is moving one way, the planet's moving the opposite way much faster. So most of the motion is with the planet. So if you have planet lines from your planet, you can look for something that is first redshifted and blue shifted in exactly the way you would expect given what you know about the orbit of the planet. So it's a way to separate out the light from the planet from that of the star, whether or not you have an eclipse. And there's a bunch of examples of this. These are actually, there are many more recent examples as well. Okay, so one thing that I like to have as an observer, I want to know, I want to do a transmission spectrum. I want to go detect a secondary eclipse for a newly detected planet. The very first thing I need to do to figure out if that's worth doing or worth attempting is to figure out what's the magnitude of the signal that I would expect to see. And so this is just a simple back of the envelope equation for these different techniques that gives a rough estimate of the size of the signal. And then the other component of that being what's the precision of your measurement. That's going to be telescope dependent, but the signal you can estimate pretty simply. So for absorption during transit, the idea is that you have an annulus of atmosphere around the planet, which is doing the absorbing or not, depending on the wavelength. So the size of the variation in transit depth depends on the thickness of that annulus. That's set by the scale height of the atmosphere. I'll talk about that more in the next slide, but then so you can just assume that the change in transit depth is the difference between the radius and the radius plus 1 scale height, which is that equation there. For the secondary eclipse, if you're in the long wavelength limit, it's just the ratio of the area of the planet to the star times the ratio of the surface brightness, which at long wavelengths is just the ratio of the temperatures. So this isn't quite right in the near infrared, but this is a good, at least order of magnitude for longer wavelengths. If you're looking at variations as a function of orbital phase, if you're looking at thermal emission or reflected light, the magnitude of that signal should always be comparable to or less than the depth of the secondary eclipse. So usually during secondary eclipse, you're seeing the day side of the planet, you're seeing the hottest part of the planet, and any other view of the planet should always be that bright or dimmer. And for the Doppler technique, which is the one that I very briefly mentioned, the thing that you care most about is the contrast ratio between the planet and the star, which you could estimate using the same equation as for the secondary eclipse. But because you're looking for lines in the planet's spectrum, you also really care a lot about how deep or shallow those lines are. And that's something that's actually kind of difficult to estimate from first principles, because the depth of those lines depend on how temperature varies with height in the planet's atmosphere. You can make a model that predicts that, but there are lots of assumptions that go into the model that can vary in detail. And so it's hard to know ahead of time which planets will have really deep absorption lines or really shallow absorption lines. And so that's going to be a little bit more hit or miss. Okay, and I'll come back to that in a minute. So one key thing here, if you're thinking about what kinds of planets are more or less favorable to observe, you'll notice that bigger planets have bigger signals. That's maybe kind of self-evident. But you'll notice that there's always this term on the denominator, which has to do with the radius of the star and also the temperature of the star in some cases. So bigger planets are easier to observe, but everything gets harder to measure when you have a big star. So conversely, you could say, how can I boost the size of my signal without changing anything about my planet? One easy solution is to imagine taking that same planet and putting it in orbit around a much smaller star. So the magnitude of all these signals depend on the size of the planet. Bigger and hotter planets are easier to observe, but they also depend on the properties of the star. Planets orbiting smaller and cooler stars give proportionally bigger signals. And so this is what's often referred to as the M-star opportunity. Okay, So I kind of waved my hands and said, transmission spectrum, the signal depends on the scale height, but I didn't really tell you what the scale height is. So let me just briefly explain that. So here is our planet going in front of the star. So this blue annulus is just the part of the atmosphere that's doing the absorbing during transit. So this is the part that's either opaque or transparent, depending on the wavelength you can think of it. So the thickness of this annulus is dependent on the scale height of the atmosphere. So that depends on the temperature of the planet. Hotter planets are going to have puffier, more extended atmosphere. It depends on the surface gravity of the planet. Planets with higher surface gravities are going to have more compact atmospheres. And it also depends on the mean molecular weight of the atmosphere, which is this mu term. So planets with hydrogen-rich atmospheres have low mean molecular weight, and their atmospheres are going to be more puffy. Planets with high mean molecular weight atmospheres, like a CO2-dominated kind of Mars-like atmosphere, are going to be much denser and more compact. So the magnitude of the signal, regardless of what's actually in the atmosphere, the 0th order thing that you need to know for determining how big or small the signal is you need to know the mean molecular weight of the atmosphere. And really what you're saying here is what's the hydrogen content of the atmosphere? Is this a hydrogen-rich atmosphere or a hydrogen-poor atmosphere? So here's just an example of a set of models. These particular models are for a super GJ1214. The exact planet doesn't matter. The idea is you take the exact same planet and you vary its atmospheric composition and you predict the transit depth as a function of wavelength. So up here on top are 3 models which are hydrogen rich. And you can see that as you increase the metallicity, the shape of the features changes a little bit, but effectively these 3 models all look pretty similar. They all have very large variations in transit depth as a function of wavelength. In contrast, if you imagine a planet with a pure steam atmosphere or a pure CO2 atmosphere or a mix of those, you can see that all of those models look pretty flat. So even though you have entirely different compositions with different features, that in a way it almost doesn't matter. The thing that matters most is that these are all model atmospheres with no hydrogen. As a result, they have very high mean molecular weight, and this annulus is very narrow, and therefore the change in transit depth as a function of wavelength is very small. So when you're picking targets for transmission spectroscopy, you should calculate the scale height, but you should also ask yourself, based on the mass and radius for this planet, do I think that this planet has a hydrogen-rich atmosphere? Does it look like a low-density, puffy planet? Or is it a really high-density planet, in which case it could have a very high mean molecular weight atmosphere or even no atmosphere at all, in which case this is going to be a really hard signal to see. Okay. So what are some of the things that we've learned from transmission spectroscopy? So most of the planets that have good transmission spectra to date are gas giant planets, specifically close-in hot gas giant planets. What you learn depends on the wavelengths that you observe at. So you can observe a transmission spectrum in the ultraviolet wavelength. And so in that case, what you're looking at is the very extended upper region of the planet's atmosphere. So you're looking at things like Lyman alpha absorption, ionized metals, and the main thing that tells you is whether or not the planet is losing mass. So is its atmosphere being gradually blown off? And you can estimate what that rate of mass loss is. So this is something that's really important for these close-in planets. If you look in visible light, you can see if you have small particles in the upper atmosphere due to clouds, maybe condensate clouds, maybe photochemical hazes, those particles will scatter light, and you can see a scattering slope that tells you something about the particle sizes and their vertical distribution. You can also see atomic absorption lines from sodium and potassium. Those are really strong features for hot Jupiters in the visible. And as you go to infrared wavelengths, now you start to talk more about looking for different molecules. So for hot Jupiters, some really common molecules that you'd expect to see are water, methane, CO, and CO2. And these are so dominant in the atmospheres of hot Jupiters that many models only include opacities from those 4 molecules. So there are other things that might be present, but they tend to be kind of more smaller contributions. And in that case, you can ask, so for any of these, you can ask what the mean molecular weight of the atmosphere is it hydrogen rich or hydrogen poor? And you can ask whether or not the relative abundances of these molecules match the predictions of chemical models, which I'll talk about more in a minute, but Travis mentioned already as well. Okay, so with secondary eclipses, you don't really sample all of these topics. So in some ways, secondary eclipses give you a complementary perspective, but secondary eclipses, you're usually looking in the infrared. So you can detect the same kinds of molecules with thermal emission from a secondary eclipse that you can detect in transit. So you can do the same sorts of chemical studies. Another thing that you learn uniquely from looking at the secondary eclipse is you can measure the temperature as a function of height or pressure in the planet's atmosphere. That's something that doesn't really have that much of an effect on the transmission spectrum. And if you look in visible light and you see a secondary eclipse, you're probably seeing reflected light from the planet's atmosphere. The most reflective things in planetary atmospheres are usually clouds. So most detections of optical albedos are telling us something about the cloud species that are present in the day-side atmospheres, although those measurements are pretty sparse. There's not very many, and the error bars are large. Okay, so for the most of the rest of my talk, I'm going to focus on one planet, because I think much as Travis did, it's nice to have a single example to think about. My planet is not a hypothetical planet. This is a real planet with real models. So this is a planet called GJ436b. This is a very well-studied form Neptune. So mass and radius similar to that of Neptune in our own solar system. It orbits a relatively small star. So the star is an early M star. It's about half the mass of the sun, temperature about 3,600 Kelvin. And that means that even though the planet goes around the star once every 2.5 days, it's a little bit cooler than the typical hot Jupiter. So the planet's temperature is only 700 Kelvin, give or take. We don't actually know what its albedo is, so it's hard to predict that temperature precisely. Okay, so GJ436 was observed at a range of wavelengths in secondary eclipse. So now this is the secondary eclipse as a function of wavelengths as observed by Spitzer. So these are wavelengths going from 3.6 microns at the top down to 24 microns at the bottom. So this is really kind of into the mid-infrared wavelength. So there are 6 different observations in 6 different photometric band passes. And from these, we can construct a sort of low-resolution thermal emission spectrum for this planet and then compare that to different atmosphere models. And so the goal here is to make some inference about the atmospheric composition of this form Neptune. So we know from its mass and radius that it must have a hydrogen-rich atmosphere. This isn't like a Neptune-sized ball of rock, so there's lots of nice puffy gas there to see, but we don't really know what the mixture of gases are. So we don't know how metal-rich or metal-poor the atmosphere might be. So now that we have our measurements, the question is, how do we actually compare those to the models? So this is where, just to sort of get into a little bit more of where the models actually come from. This is not something that I normally talk about when I talk about studies of transiting planet atmospheres. So we'll try and walk through it here. So the first thing that you need in order to make a model, and this is now mirroring some of what Travis said, is you need to know how temperature varies with height in the planet's atmosphere. So as a really simple example, if you have hot gas deeper down and a layer of cool gas on top of that, then the features you see in the planet's spectrum will be absorption features. If you have a temperature inversion, so you have a layer of hot gas over a layer of cooler gas, then you'll see those same features in emission. So the pressure temperature profile is important because it determines the shape of the features that you see, but also it's important because it determines the types of molecules that you will form in a given region of the atmosphere. Hot gas will form with the same mixture of carbon, oxygen, nitrogen, and other atoms. Hot gas will make different molecules than cooler, lower pressure regions of the atmosphere. All right, so you can calculate that. So you know what the incident flux is at the top of the atmosphere. You could assume some internal heat from the core or not. Or you could parameterize that, and you could have some smoothly varying function that you actually fit as a series of free parameters in your model. So this is sort of a theme that you'll see throughout, is with all of these parts of the model, you can either leave it as a free parameter and fit it, or you can calculate it in sort of a best guess, physically motivated way. Okay, the next thing that you need to know is you need to know what the atoms and molecules are that are present in the upper part of this planet's atmosphere. So these molecules and atoms are going to give you the opacities that affect how the starlight is distributed vertically in the atmosphere, and also they're going to create the features that you see in the spectrum. So there's a couple different choices. You can either assume that things are in chemical equilibrium, which means if I give you a pressure and a temperature, you can predict how much methane, CO, CO2, water, things like that you'll get. You can do sort of a dynamical chemical calculation, which is you have parcels of gas moving from one region of the atmosphere to another, and so you can try and kind of fold in how that is going to alter this equilibrium chemical composition. Or you can just say, I'm not even going to try to do chemistry, I'm just going to have a free parameter which corresponds to each molecule that I care about and allow those to vary in my fits, and actually let the data tell me how much of each of those molecules is present. Another big thing that is often included in models, never perfectly, is clouds. So planets are, from what we can see observationally, a majority of the transiting planets that we know of to date have some kind of clouds in their upper atmosphere. This was kind of a rude awakening. For a long time, clouds were purposely left out of these models. Clouds are really difficult to model. They're arguably impossible to predict from first principles, at least for these objects. There's just so much we don't know about their atmospheres. And so it was easier to ignore them until the data made it clear that there really were clouds and we really had to include them. And so now most models do have some sort of parameterized description of the clouds. Okay. So, all right, so you have your pressure temperature profile. So there's temperature, there's pressure. So this is a pressure temperature profile for our favorite Neptune, GJ436. We can add in some sort of ad hoc cloud layers. We can give them some particle size. We can decide where to place them in the atmosphere. And we can calculate how much of each of these molecules we would expect to see in a given layer of the atmosphere based on the metallicity we assume and based on the temperature in that layer of the atmosphere. So one key thing to keep in mind is that there's a lot of different things that can affect the properties of the atmosphere that you see. So there are sort of different components to this. So one is you want to know how radiation is sort of passes up and down through the atmosphere. That really depends on the chemistry of the atmosphere. So you need to know what are the main absorbers or scatters that are present. You can get that by assuming that the chemistry is in equilibrium. Even when you make that assumption, you still need to translate those abundances. I have this much water, this much methane, into some sort of opacity, which is what you need for the radiative transfer. I'll come back to that later on, but that opacity is actually a non-trivial part of this. So our opacities are incomplete and demonstrably wrong in some cases for many of the molecules in the conditions that we have in these atmospheres. Something I haven't really said much about is this question of dynamics. So I mentioned that these planets are probably tidally locked. So you have one side of the atmosphere that's getting all the incident light, and then you have another side of the atmosphere that's perpetually dark. There's probably winds that circulate some of that energy from the day side to the night side, but we don't know from first principles how efficient those winds are and how they affect both the temperature structure of the atmosphere, so whether or not there's a large temperature gradient, and we also don't know how they affect the chemistry of the atmosphere. So those winds can take molecules which form in a cooler region and carry them around into a hotter region where you wouldn't normally expect to see them. So you can account for these two things in a 1D model, but in order to really do the dynamics, you have to switch from a 1D model to a 3D model. That is very computationally intensive, so that's really never done in a retrieval. So any retrieval that you see is always, in some sense, a 1D model or kind of a fudged 1D, semi-approximated, trying to account for the dynamics. But when you look at these models, usually what they're doing is they're doing the radiation more or less right, they're trying to do the chemistry semi-right, and they're usually ignoring the dynamics to varying degrees, because that's the hardest, most computationally intensive thing to get right. All right, so you have your spectrum. You can model it. So in Travis's talk, he really focused on something which I would say is kind of akin to grid modeling. You have either a pre-computed grid of models or a model that you can call and compute at will, and you want to sort of step through that very limited parameter space and ask what model provides the best match to your spectrum. So typically that parameter space has only a couple of dimensions. So you're going to vary surface gravity, and you're going to vary temperature and probably metallicity as a starting point. But there's a lot of other potential variables that you can't vary because grids don't work very well once you get to higher dimensions. So you're probably working in a really simplified parameter space. That's good if your data are poor. There's no point in having a big fancy model with 100 free parameters when your data tell you nothing about the correct values of most of those parameters. This is also a good way to orient yourself. So even if there are multiple different versions of the model that would be a good match to your data, usually having a set of grids tells you roughly in what part of parameter space you should kind of focus your attention. All right, and there's some good reviews that talk about this for transiting planets. Okay, so let's take this grid modeling approach and apply it to GJ436 and see what we get. Okay, so what do we need to do to compare our models to the data? Well, let's think about what we measure versus what our models tell us. So we measure the planet's flux relative to that of the star. So we need to have a model atmosphere for the star. So all of our inferences about the planet are going to be dependent in part on the accuracy of our stellar model. So we need to have a pretty good understanding of the stellar properties. And then we also need some models for the planet. So if we're just going to do a grid modeling exploration, let's imagine just having a very simple set of models in which we systematically vary the metallicity of the planet's atmosphere, and we want to compare those to our data. So what do we actually measure? We measure the decrease in light when the planet passes behind the star. So before the eclipse, you see the light from the star and the planet together. Then when the planet disappears behind the star, you just have the light from the star. So that change in brightness is equal to the in versus out of eclipse flux. That's just the flux from the planet, divided by the out of eclipse flux, which is the sum of the flux from the planet and the star. We make an approximation. We say the star is much brighter than the planet, so we can, in our denominator, we can drop that F planet term. And then we find that the eclipse depth that we measure is just the ratio of the planet flux to the stellar flux. So I just take this model and I divide it by that model, and I compare it to the secondary eclipse depth that I measure. Okay, so this is what that actually looks like. So remember now, many slides back, I showed you 6 secondary eclipses and 6 different photometric band passes at wavelengths ranging from 3.6 all the way out to, let's see. So this is only showing 5. There's actually one more out here with a really big error bar, but here we have 5 band passes going out to 16 microns. So in black are the measured secondary eclipse depths. And then the colored lines are a series of different models with different, everything else is fixed. The only thing that's varying is the atmospheric metallicity. And so what we want to do is we have a single knob. We can dial that knob up or down and ask what metallicity best matches our data. So here, this point is the planet's pretty bright at 3.6 microns. So you can see that that seems to be best matched by the purple model, 1,000 times solar metallicity. For comparison, Neptune's atmosphere is only 100 times solar metallicity. So it would be really surprising and quite interesting if this planet really had 1,000 times solar atmospheric metallicity. It would mean that it's actually not predominantly molecular hydrogen in the atmosphere, that hydrogen is now like less than 50% by number. Okay, as we go to longer wavelengths, maybe some of these other points prefer slightly lower metallicities. So it's clear that there's no single model in this simple grid that provides a really good fit to the data. And by that, I mean a model that goes within 1 sigma of each of my data points. So it's clear that there's still some additional tuning that I need to do in order to get a good match between the model and the data. Okay, so what are some things that I might have neglected in this very simple model? And I should mention that Carolyn Morley is the one who ran all these models. And so these are all described in a paper that she wrote in 2017. So one thing that I might have neglected is I might have gotten the chemistry wrong. So probably what's going on here is my data don't quite match my models because I'm getting, I have kind of the wrong amounts of some of the molecules. So maybe I have too much methane, not enough water. You can imagine kind of fiddling with those and changing the shape of the spectrum in different band passes. So how might I fiddle with those abundances? So remember earlier I said we determine the amounts of each kind of molecule assuming that the chemistry is in equilibrium. So that means at a given pressure in the atmosphere, I go back to my pressure temperature profile and say, all right, at 1 bar, the planet's atmosphere has a temperature of 800 Kelvin. So 1 bar, 800 Kelvin, then I can go to my chemical code and say, all right, this is how much methane I expect, this is how much CO I expect, and CO2. And you'll notice that those vary as a function of height. That's because as you go further up, the pressure is decreasing and the temperature is decreasing. So the mix of the molecules is going to vary as a function of height. And it's the integrated sort of column from wherever the atmosphere is optically fixed, say it's down here, all the way up. It's that integrated column that determines the shape of the spectrum that I see. So There are things that can change that. So one thing is this planet is really close to a relatively cool star. M stars are known to be quite active. They emit relatively a lot of ultraviolet light. That ultraviolet light can break apart molecules at the top of the atmosphere that then recombine in different amounts than you would expect based on this simplified model. So this photochemistry is going to change the abundances at the top of the atmosphere. You could fold that into the model. But this also assumes that the atmosphere is sort of stably stratified, that there's not any net transport of gas from deeper down to higher up. So another thing you can imagine doing is saying, at some reference pressure, we start to have mixing that carries gas from that pressure further up in the atmosphere. So whatever the abundances are here, we have mixing, vertical mixing, that then makes those abundances effectively constant from that pressure on up. And so this is what's referred to as the quench pressure. So probably things that could cause mixing are if you have strong winds in the atmosphere, those winds generate turbulence. That turbulence is going to cause diffusion. So there are lots of different ways in which you might mix the gas, and that could affect the abundances that you see in your thermal emission spectrum. Okay, so let's say that we made a new version of our model, which includes both of these effects. It includes photochemistry, and it includes this vertical mixing in some parameterized way. How does that affect the spectrum that we predict? So here is the same model, same elemental abundances, so same amount of carbon, oxygen, hydrogen, everything else. And the only difference is now, instead of having abundances that follow these curved lines, which is the equilibrium case, you have vertical mixing and photochemistry. And you can see that what you get is a very different looking spectrum. So in particular, for the same composition, you can make the planet significantly brighter or fainter at some of these band passes. So again, it's not a perfect fit to the data, but it seems like maybe we're going in the right direction. So maybe this is getting a little bit closer to what we actually see in real life. Okay, so I mentioned that virtually every, or at least the majority of these short period planets that we've observed seem to have clouds. This planet is no exception. If you look at the transmission spectrum for this planet, it is utterly featureless, and that implies probably that it has a high cloud layer. So another natural thing you might think to add to your model is a cloud layer. So this is just a very parameterized, simple version of clouds. So the idea is that you can either have very puffy, extended clouds that have really small particles, or you can have clouds that are very compact, sort of a very horizontal cloud deck with bigger particles. So there's just a knob that you can turn that makes the clouds puffy and diffuse, or big and compact. And those clouds are placed at some arbitrarily chosen point in the atmosphere. In this case, you want them to be high enough up that they affect the shape of the spectrum. And so here's just a view of how the shape of the spectrum changes as you add in those clouds. So you can see when the clouds are these compact big particles, they're deeper down, they don't really change the shape of the spectrum much at all. So this dark blue is cloud-free, and then this purple is this sort of flat cloud deck. But as you make the clouds puffier and mix them higher up into the atmosphere, you start to move towards something which looks like this orange model. So to 0th order, the effect of clouds in all these models is to suppress features in the spectrum. Regardless of the geometry, if you're observing in transit or in secondary eclipse, whenever you add clouds, they shrink the size of the absorption or emission features that you would expect to see. And so in the case of our data, that's bad, because we actually, the problem here is not that our spectrum is featureless. The problem is that our data has these really big changes as a function of wavelength that our model isn't able to match. So adding clouds is actually making the fit worse instead of better. All right, so we've done our grid modeling. So we've done our sort of simple exploration of the parameter space. We have some maybe clues about what the answers are going to be for this planet, but this is a very ad hoc approach. It's not clear that we've actually identified the global sort of best fitting model. And even if we had, we don't know what the uncertainties are on the various parameters that we want to infer. So we might say the best match is at 200 times solar metallicity, but we don't want to know what the best, we don't just want to know the best match, we want to know what the range of solutions is that are consistent with the data. So we want best fit values, and we also want uncertainties for each of those parameters. And the best way to get that is to actually do a retrieval. And so we can do that retrieval with these self-consistent forward models. So take the same grid of models that we were looking at over here, and actually just dynamically explore this space with something like an MCMC. And so then what we could get out is something like this, where you have for every single parameter, and I don't expect you guys to read this, I'll show you a bigger version in a minute, you have some probability distribution for each combination of parameters in your model. Okay, so what does that actually look like? So this is, again, the same paper. So now you can have sort of very simple parameterization of the pressure temperature profile, which is you can tune the heat input at the bottom, and you can also tune the heat input at the top. So that's to account for things like the unknown albedo of the planet, and you don't know also how efficient heat transport is between the day side and the night side. So you have two model parameters that try and fold in those things. And then you have another set of model parameters that encompass things that affect the composition. So you can tune the metallicity of the atmosphere, you can tune the carbon to oxygen ratio of the atmosphere, and you can tune the quench pressure. So remember, this is the point in the atmosphere at which things start to be evenly mixed. So this is, you take the chemistry at that pressure, and then you just propagate that up through the rest of the layers above that. So when we allow those things to all vary as a free parameter, we can map out the distribution of solutions that are consistent with our data. And so you can see there's preferred regions of this parameter space, but in many cases there are wide distributions of parameter values that are all consistent with the data. So the data tell us more about some things and less about others. And sometimes there are correlations between parameters, and that's also important to know. Okay, so just to show you the results. So this is now the best fit spectrum here in pink with some shaded confidence interval as compared to the best sort of grid model, which is just this self-consistent forward model. And you can see when you give yourself more wiggle room and when you systematically explore the parameter space, you can get something which is demonstrably a better fit to the data. So now this model in pink basically goes through 1 sigma for all the points except this one out here, but that's still only maybe 2 sigma. So it's not actually telling you that much. Okay. So that's a nice fit to do. That allows you to much more systematically explore the parameter space, but it doesn't give you the full answer. So one other thing, if you have really good data, so say instead of these photometric points, you actually have spectrally resolved data, you can also do this last option, which is to make everything a free parameter, assume nothing about the chemistry, and instead just fit directly for the abundances of different molecules. And so Carolyn did not do that in her paper because the data weren't good enough to justify that, but an example where someone has is actually an observation of WASP 43. So this is, again, a thermal emission spectrum obtained from secondary eclipse observed with Hubble. So here the data have a higher spectral resolution, but they still have a very limited wavelength coverage. This is only 1.1 to 1.7 microns. So the main thing that you see here is you see a water absorption band in this planet's emission spectrum. And so then you can do a fit where you allow the abundances of water, carbon monoxide, carbon dioxide, and methane, all to various free parameters. And so that's water, methane, carbon monoxide, carbon dioxide. And what you see is that many of these molecules are very poorly constrained by the data. The only exception to that is water. So from these data, you can infer the water abundance to within an order of magnitude, but all the other molecules span many orders of magnitude. And that's not surprising because most of those other molecules have only a little bit of opacity at this wavelength range. So in order to really do these kinds of fits right, you ideally want a spectrum that covers a really broad range of wavelengths in the infrared with high spectral resolution, high enough spectral resolution to resolve these individual molecular bands. Okay, so I'm almost out of time. I wanted to give a few more very brief caveats that are important to think about when you do these retrievals, particularly when you think about this last kind of retrieval where everything is a free parameter and we assume nothing about the chemistry or the dynamics or the radiative transport. So one thing to keep in mind is that not all combinations of molecules are physically plausible. So imagine that I do a fit. I consider a planet with constituents for its atmosphere that include vinegar and baking soda. And I tell you that I've discovered that this planet has, equal parts mixture of vinegar and baking soda in its atmosphere. Now you can imagine if you made a real life planet with that, it wouldn't just perpetually sit there as a vinegar and baking soda planet. They're going to react with each other and form something else. So similarly, there are combinations of gases that just aren't chemically stable and that you would never expect to see in real life in a planetary atmosphere. There's also physics that you have to sort of honor as well. So sort of an extreme example, when you fit for cloud properties, these clouds have to stay suspended up in the very top of the planet's atmosphere. So if I do a retrieval and I say my best fit solution is that this planet has meter-sized boulders at pressures of 10 to the minus 6 bars, then you should really kind of take a step back and say, I'm not sure that makes sense. Similarly, you still have to conserve energy. So at the end of the day, energy into the planet has to equal energy out, and that can include interior heat sources as well. But the energy has to come from somewhere. The planet's not like creating new energy out of nowhere, and so there has to be some energy balance that you observe at the end of the day. Another thing that gets swept under the rug often is that I tell you I want to make a model with a certain amount of water, a certain amount of methane, a certain amount of carbon monoxide. The way that I translate those abundances into a spectrum is I need opacities for each molecule. There are different databases of opacities, and they can give you very different answers even when everything else in the model is exactly the same. So this is the same planet, same model, just two different databases of opacities. And you can see that the answers are different at a level that is starting to matter for the observation. You also have to bin down your spectra to lower resolution in a way that makes sense, and this is kind of a big computational problem. You can get, when your model is poorly constrained by your data, your posterior distribution primarily reflects your priors. If you thought you chose an uninformed prior, and in fact, sometimes you can, by your choice of prior, create artificial peaks in your distribution. So this is just one example, which is documented in Mike Line's paper, where you can create an artificial peak in your distribution of carbon to oxygen ratio, which has nothing to do with the data. It's just created by the way you set up your model. So I would recommend that you, for those of you who maybe haven't thought as much about Bayesian statistics, this is a really great introductory textbook that's short and easy to read. It also matters a lot that your measurements are right and that the error bars are correct. So this is the spectrum for the star from different publications. So this is the original publication. These are reanalyses of the exact same data where they get a very different answer. So your retrieval is only as good as the data and the error bars that you put into it. And here's some other good sort of best practices reviews on statistical modeling of data. So takeaway points, you can do these retrievals. You should choose the complexity of your retrieval appropriately based on the amount of information that's in your data and also the signal to noise of your data. You should always use common sense. So you can, if you have data which have underestimated error bars, or where the measurements are off, or you choose the wrong kind of model, you choose a parameterization that doesn't include the right physics, you can get an answer that seems really well constrained and is completely wrong. So think carefully about your data and think carefully about your choice of model, and ideally test multiple different parameterizations of your models to make sure you consistently get back to the same answer. All right, that's it, and I'm over time, so. If it's a hot, oh, right. How much time on JWST would you need to characterize one of these planets? So if it's a hot Jupiter, a single transit or a single secondary eclipse with something like Nearest that covers a broad range of wavelengths will give you a really nice high signal to noise spectrum. If you're talking about trying to detect the spectrum of an Earth analog planet, even around a really small star, then hundreds of hours is the right answer. Mm-hmm. No, so actually I think the bigger problem, yes. So do I have any speculation as to why this point is always high compared to the models? That one doesn't bother me that much. It's still only 2 sigma. I think the one that I worry about more is actually this point here. It's really hard to make the planet that faint because this is a really wide bandpass, and no matter how much, so this is a carbon monoxide absorption band, and no matter how much CO you put in the atmosphere, you still get a little bit of light in at the edges, and it's really hard to make that flux go down to a value that's consistent with the measured upper limit. Yeah, they do. They do. When you can, so basically you have to, I think, really fiddle with the pressure temperature profile to make that work, and whether or not that's realistic is maybe a separate question. But all of the forward models, which are not retrievals, predict the planet's brighter at that wavelength than it actually is. Yeah.
What research is going on to better model clouds?
So what research is going on to better model clouds? So a lot of, so there's sort of two different places that atmosphere models come from. One is the stellar atmosphere community, and another is the planetary atmosphere, solar system planetary atmosphere community. I think for clouds, a lot of the interesting microphysical models that people are playing around with are coming from, were developed for Venus, for example, or Jupiter. And so the idea is that right now, we just sort of throw in clouds after the fact. It's this very simple, like, here's where the cloud layer is, and here's the particle sizes. But you could, just like you can model the chemistry, you can actually model how cloud particles condense and, you know, move throughout the atmosphere. And these models are set up to do that. And the big question is, do those models, which are much more sophisticated, actually better match the data that we have? And that's maybe still an open question. So better models is one avenue. Much bigger data sets is another avenue. You can just get enough data that you can see a pattern in where the clouds are or are not. That might give you some insights as well. Yeah, so the simplest thing you should do is you should ask, how does the planet's eccentricity affect all this? So the problem with eccentric planets is the irradiation received at the top of the atmosphere varies in time, and they might also not be exactly synchronously rotating. So both of those things could affect what you see. This planet has an eccentricity of 0.16 roughly, which is not that big. So these are, I think, more minor effects, but they're like HAT2 has an eccentricity of 0.5, and that's really important. To zeroth order, you should ask what's the incident flux at the time of secondary eclipse and use that as the input to your model. Maybe there's some lag time as the heating varies, how the atmosphere responds. You could fiddle with that. You might also get tidal heating of the planet's interior. So this particular study seemed to suggest that the interior was a bit hotter than you would expect, and that might kind of hint at tidal heating going on. Mm-hmm. Yeah. Yes. So there's a lot of physics and chemistry you want to include in the models, and you really can't put it all in. The answer is that for any given atmosphere, some things are really important and other things are not so important. And if you could just figure out in advance what the important components are to put in, you could sort of toss out all the extra junk that doesn't actually change the answer for that planet. The tricky part about that is that's kind of presuming that you know the answer in advance and then make the model that kind of captures the key things, and often you don't. So you can try and run sort of you can sort of try experiments, right? So don't do a full retrieval with all the different parts of the model, but just add or take away pieces and see how the answer changes or doesn't change. And that'll give you a sense for what pieces are important or not in that case.